Hi team, this is Mr. E. We're going to be talking today about Chapter 4, Oscillations and Waves. This is the first part, Simple Harmonic Motion. The goal here is to really get an understanding of the first part of the unit. This is the syllabus we'll be following. We're going to start today with the kinematics of simple harmonic motion, which is to do with the displacement, the velocity, the acceleration, and how we work these things through to understand how things move. So firstly, what is simple harmonic motion? And what are some examples of this? Well, here's some nice examples from this Physics UNSW website. We've got a plate that's vibrating. We've got an apple like a pendulum, which is swinging. And we have a speaker moving up and down. Now, all of these are examples of simple harmonic motion. We have something moving, and it's constantly moving backwards and forwards, up and down, in a periodic way. Another really great example of simple harmonic motion that we'll be using is of a spring and a mass moving up and down. Now you'll notice as the spring rises and falls, the mass is moving. There's a rest position where it would be standing still and all the different forces would be equal. Then it goes to a maximum displacement and a minimum displacement and back again. Now we could graph this over time using a sine wave like it shows here. Now here's an example. This might look complicated to begin with, but let's just look at the purple graph to begin with. The mass is bobbing up and down, and the graph shows where the mass is at different times. We can also notice that at the ends of its displacement, where its displacement is a maximum or a minimum, we have a situation where the velocity becomes zero. So look at the top, the velocity is zero. At the bottom, the velocity is zero. Okay? So we can also map the velocities, because you'll see that in the middle, where the displacement is zero, the velocity is a maximum or a minimum. So as it's at its rest position, if it wasn't moving, that's actually when it's going fastest, when it's undergoing simple harmonic motion. The acceleration graph, on the other hand, shows basically where the forces are acting at the greatest amount. So in the middle, where the displacement is zero, the forces are all in balance. If we just had the mass sitting there doing nothing at that zero position, then the acceleration at that zero position would be nothing. So basically, wherever the displacement is zero, the acceleration is also zero. Now, why is that the case? We'll be getting into that shortly. So let's have a look at what goes on step by step. We can start off with a mass hanging by a spring from a rest position. Okay? Let's call this the rest position, i.e. x equals 0. Now if it was somewhere along this axis, up here or down here, okay, the value of where it is, let's say we pulled it down, this would have a value here of x. Now you'll notice that we have a positive x and a negative x if it's above or below the rest position. Okay, so we can define that. Now here's the thing. If you have a mass spring system at rest position and it's just sitting there, let's pretend we haven't made it move yet. There's two forces acting to hold that in place. Now we remember, if something's not moving, the sum of the forces at this position must equal 0. That means whatever forces are up must equal down. Now we know that any mass will have a force on it due to its weight, mass times gravity. Okay? Now if that was all that was there, that would mean we didn't have the spring and it would just fall. So obviously something else is going on. The thing that's going on is that the spring is just holding it up with an equal force upwards, which is the force due to the spring. Okay? And basically the force due to the spring is equal to, at the rest position, mg. So in this case, the sum of the forces equal 0. We have a down force from mg, and we have an up force from F. overall we get back where we started and the resulting force is 0. Okay, so that's in the middle where it's just resting. Now something interesting happens when we pull our spring. That was clever. I lost it. When we pull our spring down from the rest position. Let's try that now. So we have our spring system, and let's say this was the rest position, but now we have stretched our spring out down to here. We still have mg acting, okay, but now because we've stretched the spring down, the spring will be trying to pull the mass back again. The force in the spring is now greater than mg. What that means in this position is that the sum of the forces are no longer 0. Okay? And if the sum of the forces aren't 0, then because the sum of the forces is equal to the mass times the acceleration, okay, the acceleration isn't 0 anymore. The acceleration will be acting in the direction of the unbalanced force. And in this case, we have mg acting downwards, we have force acting upwards, and the force acting upwards is bigger than mg. The resulting force, okay, if we add this to this, the resulting force will be this. Okay, so overall this spring system now has an upward force, and from that upward force, the sum of the forces, okay, we have an acceleration. So the acceleration in this position will also be acting upwards. Okay? The same thing happens if we let that spring go, okay? And so here's our rest position, and now we've let the spring go, so the mass started off down here, but now it's come up here. It's gone through the middle, where the sum of the forces were equal to 0, and now it's up at the top. Okay? What that means then is the spring is actually compressed. The spring might only offer a tiny little bit of force upwards, or if it's another kind of spring, it might actually offer a force downwards. That means that mg is now bigger than the force upwards. What that means, at the top, when x is positive, the acceleration is pointing downwards. We have a sum of the forces not equal to 0, and the sum of the forces are going to equal mass times acceleration, and it will be downward, okay, because the upward force plus the downward force, okay, if this is our rest position, this will be the sum of the forces, okay? Now don't get confused, this sum of the forces, okay, is equal to what we're talking about here. We end up with a downward acceleration at this point, okay? So the acceleration is downwards, and that's what it's equal to. The mass times the acceleration is the force, or putting it other ways, acceleration is force over mass, okay? So we have a situation here. If this is our rest position where x equals 0, then when the mass is up here, okay, x is positive, but the acceleration is negative. Remember, upwards in this case, we defined it as positive. Alright? So when the mass is up here, the acceleration is downwards. When the mass is down here, we have a negative x, and we have a positive acceleration. Okay? So whatever the displacement is, in this case negative, the acceleration will be the opposite, positive. And in the middle, where x equals 0, acceleration will also equal 0. So you see what's going on here? So we've linked together now, just by looking at this situation, x and a. And this is an important thing to be able to do. That's enough for a start now. We'll move on in just a sec.